Hello, Chem 1B. This is Chapter 17, Lecture Video 8, and we're going to be doing some KSP problems now. So we can use solubility or equilibrium values to solve for KSPs, just like we have done in the past for other equilibrium constants. So if we look at this problem, a saturated solution of magnesium hydroxide is prepared. The pH of the solution, this is important, is 9.87. We want to calculate the KSP for this compound. Now the first thing to do is to write out your equilibrium. KSP equilibriums are always the solid ionic compound breaking up into the ions that make up the ionic compound. Now we're going to use an ice table. Now we have a solid on the reactant side, so we can totally ignore that part of our ice table. We initially didn't have any magnesium 2 plus or OH minus because those form as we dissolve the magnesium hydroxide. So how do we solve this? Well, we need an equilibrium state, and we can get that from this pH, right? pH gives us the equilibrium concentration of H3O plus, and I can go from that to OH minus at equilibrium, which is this row here. So if I want to do this, the first step really is calculating my OH minus concentration at equilibrium, and I can use the pH to do that. Now, we're going to fill in this ice table before I begin doing that, and we fill in this just the same way as before. Generally with solubility, instead of using X as our unknown variable, we use S. Because S is actually our solubility of the solid in the ice table. So if we just solve our ice table for S, we get the solubility. But you can use X if you want. It's just an unknown variable. It doesn't really matter. Just conventionally, we use S to represent this in our KSP ice tables. Now, one thing that we haven't seen in a while is because there's a 2 here, we have to put 2S as our change. And we'll also have to square its concentration at the end when we do the expression for KSP. It's been a while since we've dealt with reactions that aren't exactly 1-to-1 all the time, so that's going to start popping up again. So if you've forgotten about that, remember to review that. So first let's calculate our expression. I can plug that in, right? KSP here is going to be equal to magnesium 2 plus concentration times the OH minus concentration, and again, because of this 2, we have to square that OH minus concentration. And if I plug these guys in to my expression here, I get 2 times quantity 2s squared, which really is just equal to 4s cubed, right? If I kind of simplify that a little bit. Well, I need to get OH minus concentration. Well, OH minus is just really equal to 10 to the negative POH. I can get the POH from the pH, as we've learned how to do in chapter 16. And if I plug that in, I get this as my OH minus concentration, which we know is equal to 2S. So if I just divide by 2, I get my S, and I can plug S in to my equation here. Get rid of some of these arrows. To solve for KSP. I should get about 2.06 times 10 to the negative 13. So if you have any questions, let me know. Let's do another problem. Let's use KSP to solve for solubility. So in this case, we're using calcium hydroxide, and we're told the KSP is 4.68 times 10 to the negative 6. We want to know what is the molar solubility in pure water. And this pure water thing, it's going to matter later on. So for now, pure water basically just tells me what my initials are for these two. In pure water, we can assume that the initial concentration of calcium 2 plus is 0, and the initial concentration of OH minus is close enough to 0 to be 0. We're going to fill in our ice table. Again, this is going to be, for calcium, it's going to be plus S. For hydroxide, it's going to be plus 2S. Again, this 2 here is where we get the 2 in the change in front of S. And again, you can use X, Y, whatever variable you want. It doesn't really matter. We just tend to use S because it's going to be equal to the solubility. This brings us to our equilibrium row, and we can set up our equilibrium expression just like the last one, really. And this is all going to be equal to 4s cubed. And I can set that all equal to my KSP. Now this isn't actually a quadratic, it's just an equation. We can solve it. So we need to divide both sides by 4, and then we need to cube root both sides of the equation to get S by itself. If we do that, we get S is equal to 1.05 times 10 to the negative 2 molar. And this is our molar solubility. And that's how we solve this problem. Okay, so let's look at what we call the common ion effect. Solubility is decreased when a common ion is added. And what do we mean by a common ion? Well, if we look at this equilibrium here, a common ion is one of these guys. So if I add to solution an ion that is part of my equilibrium, I have just added a common ion. So if I add sodium fluoride, I've added a common ion because sodium fluoride is a completely soluble salt. It's going to break up into Na plus and F minus. And F minus is in my equilibrium. So F minus is my common ion. Now, if I add NaF, I'm adding F minus, which will increase the concentration of a product. And as we know, due to Le Chatelier's principle, this is going to cause a shift towards the reactant side. Or in other words, we're going to form more of our solid product, or reactant, sorry, if I add NaF to the solution. As NaF is added, the system's solubility is going to decrease because, if we're shifting this way, there's less of this dissolved, less of our solid dissolved. So adding common ions always decreases solubility. Now, what's important to note here is that my solubility has changed by me adding NaF, but my KSP has not. It's a constant. It does not depend on concentration in any way, shape, or form. So this is a good example of where KSP and solubility are not the same thing. So the common ion in this case, like I said earlier, is F minus. Okay, so let's move on. So what happens if I remove F minus? And first, well, how could we remove F minus? Well, if we did, right, we have CaF2 solid goes to Ca2 plus 2F minus. Well, if I remove this, according to Le Chatelier's principle, we're going to get it to shift towards the products, which means the solution, the CaF2 will dissolve more, and therefore our solubility will increase somehow if I can remove F minus from solution. Well, how could I do that? Well, F minus is a weak base. So how could we remove a weak base from solution? Well, we could add a strong acid. Remember, acids and bases, they react. So if I add strong acid, these two will react with each other, form HF and H2O. HF and F minus, they're different substances. They're not going to be counted the same. So what's this going to do? It's going to decrease my F minus concentration, thereby decreasing this concentration in the equilibrium we have going on, and therefore causing a shift to the product side, making calcium fluoride way more soluble. So in other words, because calcium fluoride is a basic salt, its solubility increases as we decrease pH. In other words, in acidic solutions, calcium fluoride is going to be much, much more soluble than in neutral or in basic solutions. And this is all due to the common ion effect and really just Le Chatelier's principle. It's kind of neat. So if you guys have any questions, as always, please contact me via email or even better, the discussion sessions. Oh, sorry, one last thing. The effect pH has on solubility is huge. This is a great way to make insoluble solids way soluble. Okay.